Welcome back to one of the videos reviewing the content for ACSL MCQs. In this video, we're going to cover the concept of data structures, which is the concept that comes out on the third preliminary exam as well as the finals rounds if you're eligible for it. So let's get right to it. So the first concept that you need to understand on the data structures unit is the concept of stacks and queues, which understandably a handful of you might not know how it applies to computer science, even though you might have heard of this term before. Well, if you understand the concept, you'll realize that in computer science, stacks and queues apply just like how it is in everyday life. What I mean by this is when it comes to stacks in computer science, you could think of it like just like a stack of books or any other items. Whereas for queues, you could think of it like the queues that you see on a music app or any other media app like YouTube, for example. So just for demonstration purposes, I'll write Spotify here. So what I mean by this? Well, it means that the way that stacks and queues work, basically these two are both called data structures. And data structures in computer science are platforms in which we store, remove, or manipulate data, like integers or strings or characters or anything that you could think of. And the idea here is that the way in which stacks and queues work and the way in which they store and remove and manipulate around the data is quite similar to how a stack of books would do that, or the queue on a music or media app would work. So let's try demonstrating this, starting with stack. And to demonstrate this idea, I'll draw a rectangular box that shows a stack of items, let's say a stack of books, and your guide trying to put in items into this stack. The way you do is the first item that you put, let's say the dark blue item, would come at the very bottom of the stack because there's nothing in it, it's empty. And if you want to put another item in, let's say a red one this time, you'll realize that it adds on top of the initially put item. So this is first one, this is second one. And you'll realize that as you progress and add more items, the last element that you put in comes at the very top. This behavior is called LIFO, also known as last in, first out. And the reason being is when you want to remove elements from the stack where you stored the elements, you'll look at the very top element that is within the stack, which is this purple one in this case. And interestingly, this is the very last element that you put into the stack. If you remove the purple element, then the green one will be at the very top, and the red, and then blue. So you'll progress from the most recent item that you put in to the oldest item that you put in. That's why it's called a last in, first out structure. That's just the way computer scientists summarize this behavior on just a term, right? Well, let's see how storing or moving data works for queues. Let's say you are trying to listen to some music. It's a phone, and you want to listen to the music in a specific order. Let's say your music app has 3 musics, 1, 2, 3, and you want to listen to it in the order of 2, 1, and 3. Well, how would you do it? Well, and if you tried like Spotify or Apple Music, you'll realize that you put in these items on queue in that specific order. So if you want to listen to music number 2 first, then you put number 2 at the queue at the very first time. And what that will do is the computer will register the second music at the top of the queue. And if you want to later listen to the first music, then you put it after that, and so on. And as you might have expected it, the queue accesses the very first element that you put in first, just like how a queue for a music app or a media app would work. And you realize that this is the opposite behavior of how stacks work. So for this type of behavior by stacks, computer scientists made up a term called first in, first out, also known as FIFO. That's just a way that computer scientists summarized the behavior of queues. You do not need to know this term of FIFO or LIFO, but they could be helpful when it comes to trying to understand and differentiate the way in which these two data structures work. And when it comes to trying to solve problems related to adding and removing data in stacks and queues, the two main terms that you need to know is pushing and popping. Basically, pushing is just adding elements and popping is removing elements. So just from our recent example of stacks and queues, let's say we have a stack, adding a book or an item into the stack would be pushing a new item, while deleting that or removing that from the stack would be popping an element out. Because if you have an element right here and you're trying to pop it, you're trying to remove it out of the stack. That's why it's called popping it out of the stack. You're trying to remove it from existence from the data structure. So the way that ACSL writes this down on the computer is for a push command, it'll be all caps push with the type or just the name of the element right here. Similar with pop, but I'll explain about this a bit later on. So let's say you have a stack, a new stack called Z, and you want to push in 7, 8, and 1. If this is a stack, then the computer will do this command first and then move in to the stack. After that, it's going to be 8, and then after that, it's going to be 1. So that means that if we are to remove an item within the stack, the very first item that the computer will see will be 1 because it's the most recent item that it was put in. And it will be the opposite for the queues. If it was put in the queue in this order, then this number right here, 7, would be the very first item that is removed out of the queue. So how does the computer know when to pop an item? What command does it use? Well, in ACSL, it represents it something like this. X or any other variable equals pop. And you might be confused at first because this basically means you're trying to attribute pop into some sort of variable, which might not make sense at intuitive side. But if you think about it, the way that this is working is, as I demonstrated before, let's say you have a stack and a purple item right here. And if you're removing an item and popping it out of the stack, then you still have this item in remainder, right? So if you want to use this item later on, if you want to access this one more time at some other point in the program, then you need to attribute it somewhere, attribute as a variable. That's why in computer command is trying to attribute it to this variable. It's trying to attribute the popped element or the popped variable into this new variable called x. And it doesn't need to be x, it could be y or z or anything, but just for most of the times, it usually stores it in either x, y, a, b, so on. You get the idea. So that's how pushing and popping works. Okay, so the next concept that you need to understand is a binary search tree, also known as a BST. And also following that, a binary search. When I write this, I'll just write BS because it's too long. Anyways, unlike stacks and queues, a lot of you guys might not have heard of a BST or a binary search at all in everyday term, especially if you have not done computer science before. And it's normal since it's not like an everyday vocabulary. But once you understand it, it'll be as intuitive as a stack or a queue, the ones that we just learned. So in order to understand binary search trees and why they're significant, we first have to understand where they come from. And to do that, we'll first read out the definition of a BST. So a binary search tree is a data structure that helps us easily locate elements, more efficient than searching the entire data. So our key focus here is easiness and efficiency. And you might be wondering how that applies in computer science, as the concept of efficiency and easiness might seem too subjective. How do we determine that? Well, it's not as subjective as you think. And to demonstrate that, I'll give you an example. By trying to do it ourselves, let's try finding data within a list of items. Let's say we have a list like this, and we're trying to find this purple orb element right here. Our job as the computer is to see at what index this purple element is located within the list, where if this is I equals 0 and I equals L minus 1, if this is the length, what index is this purple item located in? And the most intuitive answer might be to start the computer when index equals 0, right? And traverse all the way through or go across the entire list, right? And you go all the way until here because you'll know that somewhere within the list you'll have a purple item. So this is a guarantee method to sometime find the location of this element. So the computer will be like, at index 0, there's not an element, moves on, non-element, moves on. It continues to move on until it goes right here and realizes, oh, this element is at index of something. In this case, it's 0, 1, 2, 3, 4, 5. So it'll return the input of 5. And that was relatively easy, but the reason was the list or the data set that we're trying to search this item from was relatively small. What if we scaled up this example to a list that is not tens of numbers or tens of size length, but actually billions, like 10 billion, if not like 100 billion? What will we do then? Well, let's try our linear search, just like we did. But this time, our purple orb is located inconveniently at the very last part of the list. And you're the same computer that's trying to do a linear search or linear traversal. What would happen? Well, you first search here when index equals 0, but you'll realize for all the way here, there's not an element anywhere. It's not here, it's not here, and it'll move all the way until the very last element to realize only then that the index is equal to 100 billion minus 1. And that'll take 100 billion calculations. Because you have to search all the elements within the list, and that is bad with computer science, because in CS, your main focus is efficiency, how efficiently you're able to complete the same task. So that's why computer scientists were thinking like, there must be a better way than this. Computer scientists thinking there must be a better way turned into a binary search. And the idea is, to do a binary search, you need a data structure called a binary search tree. Remember how he said queues and stacks? These are both data structures. Binary search tree is also a data structure. Remember how he said data structure is a platform where you store, manipulate, or remove data, right? Binary search tree is just like that. It helps you do binary search by specifically storing items in a certain manner and certain order. So we'll see how that works and how that plays out to helping you achieve a binary search. Some of you might still be confused, so let's try doing a binary search ourselves. To do that, let's say you're a guy trying to search a certain page within a book. You have a book and you want to search a page. Let's say it's like a 1,000-page book and you're trying to find page 459. Something within page 459. What's the most efficient way to get to this certain page? And that specific day you're thinking like, oh, I'm gonna do it a fancy way. I'm gonna do using a binary search. How would you do that? Well, your first step would be to open the book, but you're not opening a book to a random page. Instead, you're opening the book to the very half of the entire 1,000 pages. So it'd be something like page 500, 501, where the left half would handle pages 0 to 500, whereas the right half would handle 501 to 1000. See how this part handles the first half, well, this part handles the second half. And what you're going to do is you're going to check within each of these halves to see where page 459 is located, if this is located at the left half or the right half. And if you look at the number, you'll know that 459 is located at the left half. It's not located at the right half. The next step would be you would abandon this right half as a whole. This would go into trash because you no longer need to search within that data, because you know for sure that 459 is not within this half. So this would go out of our searching algorithm, and we only keep this left half. And then you do the same process. Instead, you're splitting the half between the 500 pages that you have from 0 to 500. In other words, your pages would open to somewhere between 250 and 251, where the left half handles the first half, so it's 0 to 125, whereas the right half is going to handle the second half, or 126 to 251. Oh, sorry, it was already split in half, so it should be 0 to 250 and 251 to 500, right? And you check it one more time and you realize that this time page 459 is located at the latter half, this half is going to be useless. And you're going to do the same thing. You're going to remove this first half out of the search because you don't need it anymore. And you'll only keep this right half and continue the search onwards until sometime you will arrive at page 459. So you keep splitting the books in half, those mini chunks. And that will be, in essence, a binary search. You're binary searching your way to search a certain place within a data. You're trying to index the data within the data set. And some math savvy people would realize that using this method, you could achieve the calculation. You could search a data within a set at a maximum of 2 to the power of n calculations. And it might seem a lot at first, especially if you're handling a large data set, but it's going to be way more efficient than a traditional linear search. Because if you think about it, let's say you have a data and your element is located at the very last index right here. As I said, if you do a linear traversal all the way through the entire list, you will need n calculations, where n is equal to the length of the list, right? But whereas for a binary search, you'll only need 2 to the power of n calculations to achieve the same result. So I guess, just to remove confusion, let's change this variable to x, because if you sort it out that way, then the equation would turn out to something like log base 2 n is equal to x. It's going to be that because you have to do 2 to the power of n x searches to reach the value of n, the length of the list, right? So in maximum, at the worst case scenario, all you need is log base 2 n calculations, which is way less than n calculations, especially when the number n is getting bigger and bigger. You're going to handle larger and larger datasets, and in that case, you'll need this efficient way rather than a simple linear traversal. So I hope that cleared up some confusion about binary search in general. Okay, so now we know how a binary search works, but how is that applied using a binary search tree? Well, down below we have an example picture of a binary search tree that is used in the ACSL competition. And there are some things that you have to notice. The first thing you should notice is that there are a bunch of circles, and these circles within there are alphabets, which for our purposes represent the data that we're trying to store. So each of these circles store a certain data. This one stores A, this one stores M, and so on. The next one that you'll have to notice looking at the tree is that these circles are connected with a bunch of lines, right? Some span left, some span right, and all of them span downwards. The last thing is that these are all interconnected, and some of them have more lines connecting to each other than others. As an example, this circle right here, you can see that it's only connected to one line, whereas our example of E right here, it's connected to 1, 2, and 3 lines. What does that entail? What does that exactly mean? That's what we're going to figure out. So in a binary search tree, this data structure's job is to make your process of a binary search as helpful and efficient as possible. It's supposed to help you do a binary search. And the way it does it, I'll strip out an example right here, this AAM part. Let's write it here. So before clarifying how it works, let's define a few terminologies. This circle that we have been talking about, these circles, these are called nodes. Some call it vertex, but in our purpose, we'll call it nodes. And these lines that connect these nodes, they are called edges. So basically, edges connect the nodes. And this above one is called a parent node. While these two right here, these are called child nodes. And you can see the naming is quite intuitive because the parent node, that which is above right here, it's kind of like it's possessing these two lower child nodes, right? And the way it's named is that because this one is at the left of the parent node, this is called the left child node, while this one is named the right child. So the naming is quite intuitive. And the relationship between the parent node and the child node is that based on the data that's stored in the parent node, if the data you're trying to find is less than this parent node data, then you're going to move to the left, right? And in ACSL purposes, the left child node is also storing what it is equal to. So it's less than or equal to. Whereas if the data that you're trying to store is greater than the one that you're already trying to look at the parent node, it'll move onto the right. And you can see that compared to A, M comes after A in the alphabet list. Or with a more CS vocab, you could say that the ASCII value of M is greater than A. So we could tell that M is greater than A, right? That's how a binary search tree works. So let's say we're trying to search the element I within this binary search tree. How are we going to do that? Well, let's try it ourselves. We start first with the very top parent node, and the top parent node is called the root node. And let's see here. Our element I is bigger than A. It comes after A in the alphabet list. So because of that, we're going to move right. We're going to go to the right child right here. And let's look at M. We realize that I comes before M in the alphabet list. And with that, we could say that it has a less ASCII value. So because of that, we're going to move to the left. We're accessing the left child node. And now we're accessing E. As we know that I comes after E, it has a greater ASCII value than E. So we're going to move to the right. We're accessing the right child of this node. And conveniently, we now arrived at our target element I. So that's basically how a binary search tree functions and how you do a binary search within a BST, right? And in ACSL, there are mainly two things that you're going to be quizzed upon using a binary search tree. The first one is you're going to, as we just did, we're going to search data within the BST. And the second one, which is a bit more tricky, is to make your own binary search tree and then do other stuff. So when it comes to preparing this content and trying to practice MCQs, you have to make sure that you're mastering both of these contents together. And in this video, I'm going to talk about mainly some things that you might be questioned on for quite the second type of questions, which where you're trying to make a binary search tree and do other types of tasks. Well, before going into looking at examples, let's first try to make our binary search tree, because that's our first step for this second type of question, making a binary search tree. Let's take the same example of the binary search tree that we just used. This one is storing the data America, the string America. It's designed in a specific way that it sorted this data into a binary search tree. And our job is to try to see how that came to be. We're trying to replicate the same result, trying to store America, the string, into a binary search tree. So let's try doing that. The way it works is you first have the string, and your job as a computer is to look or traverse from index equals 0 to the maximum last index. You're traversing linearly, and you're putting each individual element into the binary search tree, one at a time. So let's try. The first element is A, and we don't have anything in the binary search tree as of now, so we'll store it at the very top, or the root node. Our next element is M, and our job is, as we look into the new elements, we're going to sort it into the new binary search tree that we make. And for our case of M, it's bigger than A, so it's going to store at the right child of the root node, right? Our next case is E, and we have two nodes right now. So for this one, we have E that's greater than A, so it's moved to the right child, and it's smaller than M, so it's going to store as the left child right here. And here we're going to store the new character E. So that's going to be the same process. For R, it's bigger than M. Sorry, it's bigger than M, and it's also bigger than A. So it's going to be at the very rightmost node as of right now. And for I, it's bigger than M. It's less than E, and it's bigger than it is bigger than A, less than M, and bigger than E. So it's gonna be somewhere here, right? And for C, it's bigger than A, less than M, and less than E. So C is gonna be stored here. For our final one, A is the same as A, but remember for ACSL binary search trees, it stores at the left. The same elements are stored at the left of the parent node. And uh, it might come out differently on the internet because most of the binary search trees, or at least some of them, stored at the right of the parent node. But you just have to understand the case for ACSL. Do not confuse what you see on the internet regarding most binary search trees with the type that you see on ACSL. And ACSL is stores at the left, so make sure to master that concept. Don't be tricked by it. Anyways, so we managed to make the same binary search tree as this one. And I hope that clears up some confusion or questions that you might have had regarding storing an item or storing a list of items into a new binary search tree. So let's try solving some problems now. Well, one way that you could be questioned on the concept of binary search tree after you make one is trying to search the internal or external path length. It might sound complex, but as soon as you know, it's going to be quite simple. To understand the concept, you have to first know about what a level is within a binary search tree. Because for an internal and external path length, you're manipulating this concept of levels. You're trying to use that idea. And level, you could think of it basically as how many searches do you have to do to approach that item. What I mean by this is you have the root node right here. In our case, it's 10. And let's say you want to find the level of this element 20. The way you do it is think about it. How many searches you have to do from the parent node to reach this element. And you can see how it kind of relates to the number of edges that it has, because you do one search, it goes down here, and you do two searches, and it goes to 20. So because it did 2 searches, the level of this element is 2. And understandably, because you don't need to do any searches to arrive at the very first element, the level of this element is equal to 0. So that's how you look at the levels. And you can map down the level like horizontally, because this one is level 0, these are all level 1s, these are all level 2s, level 3s, level 4s. So as long as you draw it kind of accurately, you can like map down the levels that they are located in. You don't need to do the individual calculations, right? So what is an internal path length using this concept? Well, an internal path length is the sum of the levels of all the elements within a binary search tree. So let's have an example using the one that we see at the left. We're trying to find the internal path length. So our job is to look at each of the elements, each of the nodes and their data, and see what level they're located in. Let's start with 15. We know that 15 is located at this line, and this line is level 3. So we add 3 to our answer. And up next, we are looking at level 2. And in level 2, we have one element, so it's going to add 1, 2, right? And above that, we have the level 1s. And we have 2 elements that cross this level, so we're going to have 2 times 1. And finally, we have 1 level 0, because that is the root node, so we add 0. And that leads to our answer of the internal path length of 7. So that's how an internal path length works. So what's an external path length? Well, an external path length is kind of the opposite of the internal path length. Remember how we said each node could have a child node, a left and a right child node, but not all nodes have a child node. Well, what an external path length does is it sums up all of the potential locations for the child nodes that doesn't exist yet, and it sums up the levels of those non-existing spots as of right now. So here's an example. You have this part right here. You have 5. It has a parent node, but it doesn't have any child node down here. So you will label this as a potential spot where you could have a new child node. And when you're trying to search out the external path length, you're adding up the levels that these two squares are located in. So let's try calculating the external path length. Conveniently, our box squares are all labeled up, so let's try using that. In level 4, we have 2 squares, so we add 2 times 4. In level 3, we have 1 square, so we add 3. And here we have, it looks a bit confusing, but we have 3 items. And we have none at level 1 and none at level 0. So that leads to an answer of 17. 2 times 4 plus 3 plus 3 times 2. It's the same with this answer. So our answer is 17 for an external path length. So make sure to understand the concept of internal and external path lengths, and just try to be familiar with both making, reading, and understanding a binary search tree and doing a binary search, because it helps you do the calculations way faster if you do practices. So that's it for my introductory video regarding the data structures unit. I hope it helped, and I'll post the problem solving videos at other future videos. Thank you for watching.